Hello everyone and welcome back to MV Tutors. I'm Tolo and I just want to take 5 minutes or 10 just to look at elevator physics problems. Sometimes you might find that they want you to calculate what the reading on a scale is when you are in an elevator. Okay, so we're going to look at 5 scenarios. Okay, you have a teenager there who weighs, okay, so that's a teenager weighing, how much do teenagers weigh? Let's say he weighs 65 kilograms. Okay, and first of all, I want to know, what would the reading on the scale be when he's at rest? Okay, so the elevator hasn't moved yet. It's just still. Okay, secondly, what would his weight be when the elevator moves upward, okay, at a constant speed? All right. The third scenario, what happens or what is the reading on the scale when the elevator moves downward, also at a constant speed? All right. And then the fourth option, what is the reading on the scale when the elevator moves upward and there's an acceleration? Okay. Yes, it accelerates upward, basically. Let me just rather put it like this. If there is an acceleration upward, okay? And what happens, or what is the reading on the scale when there is an acceleration downwards, or downwards acceleration? And lastly, actually, yeah, 6 scenarios. I'm just going to put it there. What happens if the cable snaps? So yeah, let's look at all those scenarios. And guys, so the scale, one thing we should know about the scale, okay, this scale, it doesn't always read the weight force. Okay, remember, if you're going to be on a scale, and if I said draw a free body diagram, what the scale would experience is your weight force, right? And there's also a normal force, okay, whether you put it as Fn or N or W or Fg. So the scale doesn't always read the weight force, okay, but what does it read? It reads the normal force. Okay, and that is why with different scenarios, if an elevator is accelerating upwards or downwards, you're not going to get a reading of the weight force. Okay, and yeah, so basically, before we start these questions, we have our free body diagram there. We have the weight force, and we also have the normal force. Okay, so generally, we would sum up all the forces in the y direction, okay? And as such, the normal force is facing upward, our weight force is downward, and we have mass times acceleration. This is Newton's second law, and this acceleration is in the y direction. We're not considering acceleration in the x direction because we're looking at an elevator moving up or down. All right, so our normal force, remember we said the scale reads the normal force. So basically you want your formula to be in terms of your normal force. Okay, so you have your mass times the vertical acceleration plus your weight force. All right, and what is our weight force? It's basically your mass times gravitational acceleration. So if I take out the common factor, I'm left with the acceleration in the y direction plus gravitational acceleration. And that is basically the formula, I don't want to say magic formula, but the main formula that you're going to use when we answer all these questions. Okay, this is, please don't forget this formula. If ever you get any question, yeah, any question, especially in the, what do you call this? The multiple section like we saw in the June paper. Yeah, just use this formula. This is your go-to formula. Okay, so with all that said, let us start with the first scenario. So here we are. This teenage boy is in a lift that has a scale. I don't know why that lift has a scale, but I would gladly hop on it. Now I'm thinking actually of taking my my scale and using it on an elevator just to see, and if whatever weight I want, I will use that one. Okay, so the question is basically which weight would I want? Would I want it when the lift is accelerating up or accelerating down? But we'll see. We'll answer that question. So A, what happens then, or what is the reading on the scale when the elevator is at rest? Okay, we go and we use our formula because remember the scale reads the normal force. All right, so if it's at rest, what do you know? There is no acceleration. There's no movement. So, this person weighs 65. So we're going to have 0 here. All right, because they're at rest. And then what we have is our 9.8. Okay, so what is 65 times 9.8? It's 637. So 637 Newton. So that is at rest. Second scenario, what if they are moving up at constant speed? Okay, let's say that constant speed is 10 meters per second. Upward. Okay, so, yeah. This is B. This is now for constant velocity or constant speed. I will say velocity. Okay, this is a constant velocity scenario. That's for B and C. When you have constant velocity, what is the main thing? I mean, when you read a question and they're like constant velocity, you're excited because you know your calculations are going to be a little bit easy. So with constant velocity, we know that the acceleration is 0. Okay. Constant velocity, therefore acceleration is 0 meters per squared seconds. Okay. So what then about our scenario for B? Constant speed. Okay, again, our normal force is mass times acceleration. Vertical acceleration, we know the vertical acceleration is 0, and the gravitational acceleration doesn't change. So again, we're going to have 637 Newton. All right. And then for C, there is what is the reading on the scale? If the elevator is moving downwards at a constant speed or constant velocity of 5 meters per second. Guys, it's constant, meaning acceleration is 0. So again, what the scale will read is 637 Newton. Okay, so this is all for scenario A, B, and C. Now, we get to a scenario where we are accelerating upwards. Ne? That's D, acceleration upwards. And let's say this elevator is accelerating at, 5 meters per second squared. And it's accelerating downwards at 3 meters per second squared. Can be any number, guys. It doesn't really matter. Okay, let's make it, 5 meters per second squared is fine. Okay, so this is now the elevator moving or accelerating upwards. That's scenario number D. Okay, accelerating upwards over here. So, again, we use our equation. Normal force, mass, times vertical acceleration, plus G. So the mass is 65 kilogram. The acceleration upward, we said it's 5, ne? Yes. So we have 5 plus 9,8. Okay, so what is the reading on the scale? Basically, we're going to have 5 plus 9,8, 962 Newton. Okay, and here in this image there, we can see that when you're accelerating upwards, you are heavier than normal. Okay, so if I'm going to take my scale, into an elevator and it's moving upward, I will not take that reading. Thank you very much. But then what happens then, scenario number E, if we're moving downward? Again, we use our normal force formula, okay, because this is the reading on the scale. Mass times vertical acceleration plus gravitational acceleration. So that's 65. By the way, I actually do weigh around the 60s. So I didn't, choose that number. It's very familiar to me. So when they are accelerating downwards, it's at 3 meters per second. Okay, so 3 meters per second plus the 9.8. But now let's just be careful, because when you are accelerating down, it'll be a negative, right? Actually, you know what? Let me use the same acceleration so that I can see. It doesn't matter what we're using. Let's just use 5 as well. Accelerating upwards, accelerating downwards. Okay. So this acceleration here, because it's going downwards, we need to put the direction as it is. So minus 5 plus 9.8. You can't just put plus 5, because now we're going to get the same reading. Okay, so if it's minus 5, we're going to go back. Now we have 312 Newton. I actually just thought about it. The scale will actually read your weight, your mass, sorry. It'll not read your weight. So it doesn't matter whether the elevator is going up or down. I'll always be that 60 something. Okay, so yeah, so we can see then when you are going or accelerating downwards, you actually feel lighter than normal. And I don't know if you've ever felt it when you're in an elevator. When it goes up, there's just, I don't know, does your stomach like feel a little bit funny and you feel a bit heavier, as opposed to when it goes down, actually feel light. I don't know, just next time you are in an elevator, please just be aware and ask yourself, like, do I feel lighter? Do I feel heavier? Is this thing true? So yeah, basically that's that. A person would feel lighter than normal when an elevator is actually accelerating downwards. All right. Now the last scenario that I wanted to have a look at is, what if the cable snaps? Okay, so if the cable snaps, then it means that elevator is actually in free fall. Okay, when you are in free fall, think about being in space. Well, we've never really been in space, but think about it. Like, but in space you don't really have gravitational acceleration acting on you. You're just floating about. But yeah, if an elevator snaps, it's actually going to be in free fall. And we know that in free fall, the only force that's actually acting on you will be the gravitational force. Okay, so if the elevator is in free fall, both the elevator, okay, and this teenager, all right, will actually have or fall under the same downward acceleration. Okay, so both elevator and teenager will be affected. Let me just put it like that. Will be affected by G, okay, the gravitational acceleration. All right, and at that point in time, because there won't be contact, because if you think about it, if it snaps, you will sort of like float upwards a bit. So there will not be any contact between this teenager and the scale. I'm just going to say boy. Between the boy and scale. Okay, there won't be any contact. And if there's no contact, then your normal force is just going to be 0. So there will not be any reading on the scale because there's no contact. Remember, the scale reads the normal force, and in order for you to have a normal force, there has to be contact. All right, so yeah, and that's it, guys. That's basically that. Those are the questions or scenarios I wanted us to have a look at with these elevator physics problems. They're so easy to forget. Hence, I decided to make a video so that we can always remind ourselves. But anyway, thank you for tuning in. Do not forget to like our videos and also subscribe to our channel. Bye.